someone that some of us already know him, and we visited him last year. She worked in physics biology or physics in biology, studied the propagation of action potentials into the nerve cells, and after the PhD degree there in the Yaoundé University, she moved this January to visit Jürgen Kurz at Potsdam at his Institute of Climate
Impact.
Yes, sir. And she will be there until the end of the month, and then she returns. She's missing Cameroon a lot, at least the weather. Because with minus 25, she cannot survive for the constant. But thank you very much for coming, and she's going to talk about this, the propagation effect in the nerve cells. Thank you very much.
Okay, thank you for giving me the floor, and I'd like to thank everyone for giving me the opportunity to be here to present you some of my work. What I would like to share with you today is a part of my PhD thesis, and the topic is effect of propagation on the generation and propagation of action potential in a single nerve cell. An important need of organism is the communication between and within the cell. Is an important fact to be well and during all our state. Is how the most studies are focused on the study of action potential, because a nervous cell is a fundamental element in the brain, and is an important property is conduction and excitability. So, some study will be done in the generation and preparation of action potential. We have the study of Inza, who have studied the non-synaptic propagation and the generation within the parallel cell. Other study is the study of Rotsky, who have studied the effect of imperfection of ionic channel. This study is a general fact in the generation and action potential. A particular fact is that if the neuron are affected, how is the action of this defect in the propagation of action potential? This is a main problem of our study, and we want to study the effect of this perturbation on the generation and propagation of action potential. You need to generate and after to propagate. Okay. Those outline is we present different mathematical models, and some of many mathematical models, and we present the influence of perturbation in generation. Without this study, we present the effect of the proper perturbation of neuron. You can have an external or internal defect. External defect, you can have an imperfection of ionic channel or delineation. Or you can also have an external or effect of electromagnetic field. Only this kind of pointer has an effect in my organism. Okay. The first part here is to present some different mathematical models. And we present here the generality on the different biological signal. We have bioelectric signal, who is the signal produced by the cell, the organism, and so on. And this part is the signal we study in our work. Now we present some different mathematical models. I don't present some biological effect of the neuron in this line. I present only the electrical model of a nervous cell. We consider a nervous cell like an electrical cable, and we give the equivalent electrical model, and this is given by this figure. Here we have this is CM is a mapping capacitor. I don't present any detail on the exchange of ionic and so on. I present only the electrical circuit. We have a mapping capacitance and ionic current and so on. And here I can also I can evaluate the current flowing on this circuit by using the Kirchhoff flow. I have the equation of the current flowing in this part of membrane. V is the different potential, and the first term is the current flowing through the membrane capacitor, and we have a unit current E, Na, K, and L. Na is for the sodium ion, potassium ion, and for the other ions present in the cell. The important fact here in this model is to determine this part, the unit current, because this is the membrane and the current flowing through the membrane, and this is very easy to determine. This is an important factor to generate to model the action potential. And for this there are many studies, and the first is the model of Hodgkin and Huxley, who are the first to model the action potential of action by giving the expression of of unit current by this relation, where J is a membrane for a channel E, unit channel E, and VE is a difference between the potentials at this node. Where they have shown that this unit current can be done by the following equation, where M and N are some probability. I don't explain the different meaning of M and just to show the general model. Okay. In fact, the equation of unit current flowing through the membrane capacitor is given by this equation. After determining the unit current, we have this equation, and equation of N, M, and N. This all four equations constitute the Hodgkin-Huxley system, and to analyze this system is very complex, because we have many parameters to take into account, and we have for the complexity of the organism, we need to have many parameters, and it's why there are some other studies who have reduced this system. And we have, for example, we have the Fizzo-Habomo model, who reduced to the four equations into two equations. And so on, until we have obtained only one equation, and this equation is in the case of the action potential in the myelinated fiber. This is the structure of a myelinated fiber. You have here is the axon, and this axon will have a myelin node around the axon of our action potential, and only this part is concerned by the model, only this node, and this is a part who is responsible of the action potential, because here we have a higher resistance, and the current don't flow through this part. And that both this equation and by this circuit represent only the equation in this node, and by coupling it, I have a discrete equation given by this one. I done some modification, some adjustment to have this equation. I don't mention that here. I just only present the general equation for the myelinated fiber. We have a discrete equation, and is the number of the node where I present in the last slide. Okay. Now after present some general, briefly some modeling of action potential, and now we want to focus our attention the effect of other some perturbation in this action potential. Now, here, the problem is first to do what? I want to know if any neuron can generate action potential. If I receive some excitation, in which condition I can generate an action potential. Okay, for this part, I done some mathematical equation in the last model. I don't present it in this one. I just consider a signal. I just consider my signal like a Gaussian signal, and I introduce it in my system. I consider the amplitude and the large of my signal to have the condition in which case I can have an action potential. Okay, here A and K are the A is the amplitude and K is the length of my pulse. Okay. Yeah. The length. Okay. Thank you. The length of my pulse, and this is the equation of A and K for which I can have generation of action potential. This is in the case of normal condition. I don't have any perturbation, and I plot here A and K. For example, if I am in this side, one means what? If I take A and K in this part, A for example equal to 2, K equal for example to 1, I can have a generation of action potential. If I introduce this Gaussian in my equation, I can have a generation of action potential. This depends on the intensity of the excitation. Which intensity of the excitation can produce the action potential? This means of this figure. And now I want to improve the effect of my perturbation in this figure. When I have some perturbation, what is the difference between this domain and the other one? In this case, I can generate an action potential or not due to the perturbation. This is the seat of our work. And yeah, this figure is just to present for this is my initial signal introduced in my medium, and this is the generation of the action potential. And the other is not the generation. This is the same figure at different times. I don't have a generation of action potential. Okay, now the important part is here to focus on the effect of perturbation. Here I delineate a region in my nerve fiber which is perturbed, and this is the region is imperfection. Here I focus my attention in the proper inner imperfection. This means that the neuron disease, I can have imperfection of unit channel. For example, I can have some protein who can block my channel, and I cannot have a very exchange between inner and outside of the fiber. This is the effect I want to study in the generation of the action potential, and I can have a local perturbation like this, or I can have a random perturbation, which means that I can perturb this node and so on this node, or I can perturb regularly the node. And in the real life, the real case is the case of random perturbation. I cannot have exactly this region. I cannot say that exactly this is the region of the perturbation. I have the random perturbation. Okay, I always present the case of regular perturbation, and this is the model of my unit channel. I consider the conductance of the only constant, and this is J here is the perturbation, J0 is the conductance without perturbation, and I introduce in my system this this function which depend on, which is a Dirac function. X0 is the, X0 is for example this channel. If I am here, this is X0, Sorry. Okay, I can have this case where J is equal to this function. This is the case of regular perturbation. Or I can have this one where J is this function. This is a random perturbation. Rn is a random number. Okay, and N is the set of perturbation.
What is that random number? What does it measure?
The random number vary between 1 and 0.
But what is the meaning? Because the J defines where you have the perturbation. What is the meaning of R there? If the perturbation is big or small, or
no, the meaning of R means that I don't have a regular perturbation.
So R is either 1 or 0 only.
Yeah, R means what I can have here or here, and the perturbation is.
So R is an integer number.
Yeah, it's between 0 and 1. Yeah. Okay, here I do the modification. This effect of J have the modification in the equation of A and K present previously in the previous slide, where A and K is the amplitude of length of my choice introduced in my medium. Okay, and this equation, this is the case of random distribution, and the last is the case of regular distribution. And I also plot the domain of generation of action potential. Remind that this epsilon is the intensity of my perturbation, and this for epsilon is equal to 0. I have the domain of where we don't have the perturbation, and I note that where epsilon is positive, I have this is the domain of perturbation. This is for the value of epsilon, the positive value of epsilon, and for the negative value of epsilon. This domain increase when epsilon increase, positive or negatively, and this is for epsilon negative. I have the reduction and the decreasing or the increasing of the domain of my perturbation. This means what? Biologically, when I have some perturbation in my system, I can have this result have an impact in the neuron sensibility. When if I receive an excitation, in which case I react the time of reaction. This influence the time of reaction. I can the reaction can be slow or hot.
The difference between the negative and positive value of epsilon is related to depolarization or hyperpolarization of the node there?
The positive or negative value of the node means what? In this figure, I can have in this figure, please. Here means that I can have a large channel or a small. Where we can have a deposit of some protein here. You can have a large or reduced channel. This is the meaning of epsilon, positive or negative.
But now the modification of the channel is always the same, but it's randomly distributed along your fiber.
For the randomly distribution, I don't consider the fact that if this channel is so large or reduced, I don't consider this fact in my study. I consider only my distribution is randomly along the fiber. I don't consider this case in my work. Now I say that this effect of the perturbation has an important effect in the neuron sensibility. We can be hypersensitivity or hypo. We can be upper and or hyper and or hyposensitivity. Okay, this is the main importance of this is the consequence, the biological consequence of this result in the nervous system. Okay, here we have the epsilon is equal to 0, we have the theoretical consequence of our result. We have the increase of neuron sensitivity or the decrease of neuron sensitivity depend on the sign of epsilon. Now this result is the main result of our work, and now we want to consider the effect of the delineation. We have the same result, and I don't want to improve in this fact. Now I want to show the other effect, the effect of external environment. Means I consider this effect by introducing an electromagnetic field in my system. Now, when the one is under an electromagnetic influence, we can have modification of our system. Our system is completely modified, and here we present our result on the case on where you consider we consider the amplitude of our field and the frequency of our field. Here, our attention is focused only on the amplitude of our field. In which case, in which amplitude of our field, we can have the perturbation of the generation of action potential. And here, this figure is showing the same case where we value our A0 is a amplitude of our electrical field. With electromagnetic field, but in this case I consider only the electrical field. I don't now introduce the magnetic field in my medium. And this is the effect of the electromagnetic, the amplitude of electric field in the domain of the generation. I know that here I have the increase of the domain of perturbation. When the amplitude of my field increases, the domain of perturbation increase. This means that when I am exposed in the higher electromagnetic field, I'm very excited. This is the mean of my result. Okay, and this is the biological mean of this result. The higher electromagnetic field induce the higher excitation of the nervous fiber. And this is the same result for the case of frequency change. And this is the biological field. And this result in accordance with the one of Random, of Hartmann, who has done the same case, but considering also the effect of the frequency in the sensitivity of the neuron. Now, I want to improve another case of another consequences of the perturbation in the action potential generation. After generating, we propagate. Okay, if I cannot generate, I cannot propagate. If I generate now, how is the propagation? How is the effect of this perturbation in the propagation now? And the main important step in the propagation is the velocity. Okay, and now I focus my attention in the velocity of the action potential. I know that we can have the different neurons have different speed velocity. If I have a myelinated neuron, the speed is higher than the speed of unmyelinated neuron, because in the myelinated neuron we have the myelin shell, and the action potential don't act in this part. Okay, now I want to present the effect of the ionic channel in the speed of propagation. Is the next part of my study. And here I consider the modeling of my ionic channel by this equation. This equation means that this is the graphical representation of my equation. I consider the zone where I done some modification in my system. This means that in the action in the nerve fiber, it's the same case like the one presented in the next in the next slide, where I have a neuron with the delineated zone of perturbation. And now I want to show the effect in the propagation speed. Okay.
This J represents the conductance through the nerve or along the nerve?
Along.
Along.
Yeah, along the neuron, along all the axon.
Okay.
Yeah. And this is the speed of the action potential for, yeah. This is the speed of action potential in the case of perturbation. The value, this value of speed, the speed of action potential is around 28 meters per second. Where I introduce my defect in the neuron, I have this reduction of the speed. This is R is the biologically R refer to the intensity of the perturbation. If it's higher or if it's is the mean of R. And when this R increase or decrease, I have the reduction of the speed propagation. In some case, I can have a slight increase of the speed, and this case is not really show for other case of R. This due source maybe due to the complexity of the system. And the general result here is that when when neuron is under the perturbation of ionic channel, I can have the reduction of the speed. And this you can have also until the failure of condition for certain value of R, which means that neuron cannot conduce the action potential. Even if you excite or a large number of excitation, you cannot have a reaction of neuron. This is the mean of failure or propagation failure.
It looks from there. It looks that you have some range of R for which, for positive values, you have a lower speed. For negative values, you have a lower speed.
Yeah.
But there is it seems to be an optimum value of R for which the speed is maximum.
Yeah.
Which in your case is 0.5.
Yeah.
So
it's
like a parabolic shape of the speed as a function of R.
Yeah.
At least there.
Yeah. Only for this value of R equal to 0.8. Only for this value you have this slight increase. For all other value of R, we have a decrease of this. I say that this is maybe due to the complexity of the system. You have this slight increase of the speed propagation. This is the explication I found for this value of R. All the other values lead to the decrease of R. When R is positive, we need to have a higher value to lead to the propagation failure. We have here 1.2, 1.6. Or when R is negative, we quickly have a propagation failure. Yeah. Okay. And now we want to show here this is not very, it's the same result like the case of imperfection of initial. I can pass this result just to show how I can consider the imperfection of initial in my delineation in my neuron. This is a neuron, and I can have some disruption in regular disruption, or I can have complete disruption of myelin. This depends on the intensity of the perturbation, and we have the same result like the one of imperfection of solution. It means that we have the reduction of velocity until you can have a propagation failure. And this is the figure present in this case. And now this is for the case of stochastic. We consider stochastic regular distribution of the nervous of the perturbation. And this is the figure we obtain in the case of stochastic distribution. And the biological consequence is the propagation failure. Propagation failure is a very important problem of in the nervous system, because when you receive an information to conduct in the other part of the system and you cannot conduct it, it can cause many disorders in the nerve, in the brain. And the propagation failure is at the origin of many diseases, like for example Alzheimer is the effect is the one consequences of propagation failure. And this is the consequence of the imperfection of ionic channel or the demyelination in our nervous system. And now this is the biological result of our work. And now we want to use this result to some application, technological application. We can use the same model of neuron fiber to, for example, model an electrical, nonlinear electrical cable. Why? You know that if you have a non-linear or linear electrical cable, it's more expensive to consider only non-linear component, because non-linear component is so difficult to manufacture. If this is the case of the biological application of my study, in the technological application, here I consider the model of myelinated fiber. This part is N1 is a non-linear part. This is a myelin sheath. N2 is a non-linear part. Is a random node. If you remind I present some myelinated neuron with we have a myelin sheath, a random node, myelin sheath, random node, and I model this myelin sheath by a linear part. Non-linear part by a random node, because we have a complex behavior here in the nonlinear part. And if I compose all this part, I can have an electrical line transmission, because this nonlinear component here I have an electrics of linear component. I have C, A, and G. It's easy to manufacture this part like this one, because we have here a nonlinear component, and it's very difficult to manufacture it. Not difficult, of course. This one is low. Is difficult. Is expensive than this one. And this is an important part due to our country. My country is we call PPTE. This means poor and very indebted country. Pays pauvre très endetté. This is the fact that we need to do some technological application to improve our work. And if I consider this electrical linear cable, it's very low cost to manufacture it. That in the case of if I have only non-linear component, and this is the same model of a myelinated fiber, and this can help me to manufacture this non-linear electrical cable. So I present some result of this work, and it's not very important to present to here today. This is the technological application. Please. This is a technological application. We can have the manufacture a non-linear electrical line cables composed to linear part and non-linear parts and so on. And also we can have an artificial neuron. Also due to this one, we can use the artificial neuron to some biological technological application. And here we focus our attention in the study of myelin, and our aim is to have our proper our artificial neuron. Considering this work, we can be able to have some component to manufacture our own, to have some linear and nonlinear components. We can have the same behavior like a biological neuron. And so, to conclude with that, we have done some biological effect of the neuron of the perturbation in the generation of action potential, and we have done some biological effect of the external perturbation in the speed of propagation, and we can show that we can have a propagation failure in the case of higher perturbation. And we also show some technological application of our work in the case of manufacture of nonlinear electrical cable. And this is some publication of this work. The two first and the last is the study of our actual study in the case where the first is in the case of a single neuron. And we know in the brain all the neurons are interconnected, and now we have now coupled two different neurons, and this is the actual study we done in the collaboration of Professor Post and Dr. Mawan in Potsdam. Okay, thank you for our attention.
Any question? I have a question because, in my opinion, every time you reach a Rambian node, what you do is more or less an amplification, because there you recreate an action potential, somehow you amplify what is coming. Yes. What's the difference of having a linear transmission plus an amplification with respect to your model of the linear and non-linear nodes?
Linear and non-linear node.
Yeah, well, you have a linear is propagation,
yeah,
actually,
yeah,
with some losses.
Yeah.
And then you have a non-linear part, but that non-linear part is basically an amplification process.
Yeah.
What is new with respect to the typical lines, propagation line they use for instance in electrical circuit, that they have amplification and they have linear transmission also.
This is not only
Well, your model of linear and non-linear chain.
Yes, just to say that I can have a low-cost electrical line fiber, because I have a linear part is not difficult to manufacture the non-linear part. Mm-hmm. Yeah, just to have this is the same model in the myelinated fiber. Mm-hmm. We have linear and non-linear part. Some studies have been done in the case of myelinated fiber, where we model a myelin shirt like a linear part, and model a rounded node like a non-linear part. Mm-hmm. And this is the same model in the case of electrical line transmission.
I see. Any other question? Well, if not, thanks again. Welcome to Mallorca.
And very good city.
So you are yesterday or no?
Yesterday.
So you're staying there all the month until you get until the end of March?
No, at the beginning of April. I also have 1 month.
¿Qué pasa?
Good.
Hola.
Hola. ¿Qué tal nuestro español? Muy bien. ¿Mejor que el alemán?